Hello everyone. In this lecture, we are going to see ASME Section 8, Division 1, Hand Calculation, as per UG 28, Thickness of Shells, under external pressure. We have all these courses available on our Thinkific platform. To learn more about these courses, register with the link given in the description.
Let us take one example. Now, what thickness I should take? Okay. So I'll give you the value. Okay. The required thickness which we calculate, these are the result of internal pressure. Okay. This is the result of internal pressure calculation which we did for the same values for same pressure vessel. Okay. So the required thickness we got after calculating from the formula was 14.67 mm. The design thickness, which we call after adding that corrosion allowance. Okay. So the design thickness we got 17.6 mm. Guys, please also understand the different terminology which we use in code. Okay. And in normal language as a static equipment design engineer. Required thickness, design thickness, nominal thickness. Many times we get confused with these terms. So please note it down. So required thickness 14.67, design thickness 14.67 plus 3 mm, which is 17.67 mm. So if this is the thickness I need for design, I took a nominal plate, right? Because we won't be getting all the thicknesses in market. So we get some standard plate thickness. So in this case, I got 18 mm plate. Okay, so that we call as nominal thickness. Now you have these thicknesses available with you from internal pressure calculation. Now you tell me what will be the thickness you will assume. See, you can assume anything. Code is not prohibiting. Okay. But if you select wrong thickness, you may end up doing lots of iteration, okay, which may not be required. So why to go for iterations? Select right thickness. Okay. So anybody can tell me if with this data, what will be your starting point? What thickness you will assume and you will start with. See, there is nothing wrong in this. Okay. I'm just talking about good engineering practice. As a static engineer, what I have developed, when many engineers follow, that is what I'm talking about. That is based on completely your engineering judgment. Okay. So Mahendra Singh is saying 16 mm. Sanjay ji is saying 15. Munendra is saying 15. Okay. Come on, guys. Mahendra is saying after removing corrosion. So, but Mahendra, your answer was 16. So if I took 18 mm as nominal and removed 3 mm corrosion lines, I'll get 15 mm. Hasin is saying 17.67. 18 corroded. 18 is not the corroded thickness, Manoj. Okay, you can see here. Nominal thickness, if it is 18, 18 is not the corroded. So 18 thickness after corrosion, what it will become? 18 minus 3. Aditya is saying required thickness 14.67. Okay, lots of variety. So the right answer is, I will start with 18 minus 3, which is 15 mm. Okay. And why I'll start with that? Because at the end of the life, my vessel is going to be 15 mm. If that, see 18 mm, I have to provide. I cannot provide less than 18, right? Even though my external pressure, the thickness required is not that high. Okay. But if I am able to qualify that 15 mm, which is at the end of the vessel life, I'll get 15 mm. So if at the end of life, if that pressure vessel is able to sustain that external pressure, I'm good enough. Right? So getting it, guys? Say yes if you got it. Say yes in the chat box if you got it. Why I'll select 15 mm? You can select any, right? But with engineering, if you follow this, you will end up with less iteration. Okay, that is the only point which I have to say. Okay, great. So now we know what is the thickness assumption I should make so that my calculation will be faster. Okay. So I assumed 15 mm. Okay. Now let us move with the calculations. Now I know you will be able to find the outside diameter, because now if we know this thickness, now somebody maybe even get confused with whether I should take 18 or I should take 15 to calculate the outside diameter. Tell me guys whether it is correct, or you are thinking of 15 also. Murin is saying correct. Anyone is thinking 15? So if you're thinking that, I will explain why not. Okay, Veera is saying 18. Great. So Rajesh Shekhar is also saying 18. See, people sometimes may get confused that, we take 15. See, 15 is the corroded thickness. Okay, I accept that. We assumed also 15 mm as the starting thickness, but the OD is not changing, guys. Okay, the 18 mm nominal thickness which I took in the start, and I rolled the vessel, I made ID of 2000. Okay, and then the OD was completely painted and there is no corrosion happening at the OD. So OD, which was 2036 in the start, that is not going to change. After corrosion loss, what is changing is ID. ID will increase to 2006 if corrosion happening, not the OD. So OD is not going to change. Got it, Mahendra? Okay, I know this query will be there, so I clarified. So I hope I clarified to you. Just think about it. Okay, if still you have not understood, great. So 2036 is the OD which we will take. We have calculated that. With this OD, we have already the thickness. Okay, now you don't get confused with 15 here, 18 here, right? Now I think you remember. This is the corroded thickness because we are calculating for end of life. Here we used 18 because OD is not going to change. Okay, so 2036 divided by 15, we got 135.73. Remember this value because we are going to use this value for calculating factor A. Okay, so we have D naught by T. What other ratio I need to find? That is L by D. So see, now based on D naught by T, I will be able to find that methodology 28C1, which we used already started, but now it is complying that, okay, we are following D naught by T we have calculated. Now we are trying to find L by D. So L, we know that tan to tan length plus 2 into H by 3. H is the depth of the addition. Okay, so in this case, this is the depth 4000, which is the tan to tan line, 2 into H by 3. H in this case, that will be based on the type of addition you have. Okay, so that is one more thing. It is very easy to find for 2:1, but torus spherical, you need a proper formula for find out H by 3 or the depth of the addition. Okay, so elliptical, it is ID by 4. So 0.25 ID is the depth of 2:1 elliptical. So now what we got as a total L for external pressure is 433.34 mm. Now I have D naught by T ratio, I have L by D naught ratio. Where I'll go now? Tell me where I should go now. Once I have these two ratios, where I should go now? Subpart 3, figure G, exactly. Okay. So this is the subpart 3. We have recreated it based on ASME code. So directly don't use it, but similarly it will look, if you open factor figure G of code, it will also look very similar. Okay. So now this side, if you see, this is L by D ratio, and the lines which you see here, it's D naught by T ratio. Okay. So L by D, D naught by T. Now wherever that L by D intersects with D naught by T, you will get factor A. Okay. And this is a logarithmic graph. So you have to be very careful while reading the values. Okay. Now what was our L by D ratio and D naught by T? L by D was 2.1. Okay. And what was my D naught by T? My D naught by T was 135. Okay. So 2.1 and 135. Let us try to find out the factor A from this graph. Okay. So for that, what we will do? First, I'll draw a horizontal line by taking 2.1. Okay. Yes, you can see here this side L by D ratio, L by D naught ratio. So 2.1, I'll draw a complete horizontal line. Okay. In the second part, D naught by T. Okay. So 135, which is it will lie between these two lines. I have D naught by T ratio 125. There is a line available in the code. For D naught by T 150, also we have a line. Okay. So 135 will lie in between. Now you know that it's approximation which we are doing. Okay. We don't know the exact because there is very small gap available. Even the thickness of the line will also try to vary. Okay. The exact value still vary based on the thickness of the line also. Okay. Because now what I will do if I want to find the exact value of factor A, is there any other method? If I don't want to refer this graph, okay, and I want to find, because graph will not give me the exact value of factor A, it will give me the approximate value. Anybody can tell me what I will have to do if I want exact value, if I want to calculate the exact value? Yes, Manoj, exactly. We can use tables. After this graph, if you see in the code, once these graphs are over, you will find tables for all these ratios. So you have to be very careful. We will see, not in this class, but later class, that how to use the table, how to use the interpolation. Many times we'll get confused how to use it. So we'll see, it's easy. Just you have to do it one time. Okay. After that, it will become really easy. So we are trying to figure out the approximated factor A. So this is the line for D naught by T, and this is for L by D naught. So it's intersecting at this point. So I'll draw a vertical line. Okay. And I'll find the factor. Now tell me what is the factor A value. Okay. Tell me how you will read this factor A value. What should be? Okay. Stack might have already seen that value, which is given here. Okay. 0.0003. Okay. So how you read it? Because it's logarithmic, you see here it's this line is 0.0001. Okay, this point, it will be 0.0002, 0.0003, 0.0004. That is how we read it. If I have to read this value, it will be 0.002. Okay, this is how we read it, because it's logarithmic and it works in a multiple of 10. Okay, yeah, it can be 0.00038 or 39, right? So it's a approximation which we are taking. So that much variation is possible, right? Great. So now once we have got factor A, now tell me where I should go. Once I have found factor A by using section 2 part D sub part 3, what should be my next step? Material chart. Exactly. So I'll move to now how to see which material chart is applicable for me. For SA 516 grade 70, let us say which material chart is applicable. Like if you see after figure G, you will see material chart CS1, CS2, CS3, like that. How you will exactly find out what is the applicable material chart for my material? Who can tell me? Tell me full, right? Himanshu, tell me full, not only part D. In part D where? In part D where I'll go? Subpart 1, right? In subpart 1, there are stress tables. Correct. Now Munindra has clearly. Subpart 1, table 1A, which is applicable for section 8, division 1. There I'll find out my material, SA516 grade 70. In the same table, you will find the applicable P number, group number, and also the chart number. Okay. So if you see the different lines which are there in the table 1A, you will find the applicable material chart. So with that, for 516 grade 70, it's CS2. So once you go to section 2, part D, sub part 3, after figure G, you will have first chart as CS1, then CS2. So you have to go to CS2, okay? And then in CS2, the graph will look like this, okay? Here we have factor A at the bottom, and horizontal line will represent factor B. And there are lots of lines like this, okay? These are what? These are temperature lines, okay? And at each and every temperature line, there is modulus of elasticity value also indicated, okay? So if my temperature is up to 150, which is the case in this example, so I'll have to follow this line, okay, which is of cyan color, okay? So this is the line which I have to follow. Factor A already I know. So what first I'll do, the same factor A, which is 0.00038 or 39, at the same location, I'll draw a vertical line. Okay. This vertical line, whenever it touches this temperature line, that point I'll draw a horizontal line. Okay. So this horizontal line will indicate the factor B value. Okay. So in this case, what factor B I should read? In this case, tell me, what is my factor B? Come on, guys, just read from here. What should be my factor B? Right? You're close, 23, 22, whatever we take. Okay. But this graph is recreated. Okay. So it's little different than what you get from ASME. Okay. So if you use section 2 part D exactly for the factor A, which is 0.00038, you will get factor B as 40 MPa. But you were exactly right once you are trying to read. This is how we read. Okay. But this graph is not exactly the same. So we are not getting the exact value. Okay. So in actual, we'll get 40 MPa. Okay. So if you are using this just as an example, you can even take 22 or 23 MPa value. Okay. So in this calculation has been done based on 40 MPa. So we'll go with that. Okay. I hope it clarifies. So now we got factor B. Factor B is 40 MPa. Whatever value is you saw as a factor B, that is in MPa unit. Okay. So whatever you get as a factor B is MPa value. Okay. Based on this factor B, code is giving you formula that based on this factor B, I can calculate the allowable external pressure, PA value, by using this formula. Apart from B, there is D naught by T, which is already we have calculated. Okay. So based on that, I can easily find my PA if I substitute the values of B and D naught by T. I got 0.039 MPa. Now tell me whether this PA is acceptable, whether this allowable pressure which I have got, with this, can I say that design is safe, or I need to do iteration? Whether this is end of it or I need to do some iterations. Ajay is saying safe. Okay, safe. Why we are saying it's safe? Because this allowable pressure which we got, that is saying that what maximum pressure external as external which can be applied on the same pressure vessel, the geometry of the pressure vessel which we have taken as an example. So for that 0.39 MPa it can take. And what was required? as a design, 1 bar, 0.1 MPa. So it can take more pressure than what is required. Okay, so my design is safe. Getting it clear to everyone?